So last time we managed to show Compactness theorem. Let me recall the statement. So it said that if a theory was finally satisfiable, so any finite subset has a model, then the whole T has a model. Okay, today I have first some comments which make sense after stating general comments related to compactness theorem and topics around it, and then we will finally get to proving these theorems MT1, MT2, which were necessary for access theorem and Hilbert-Nullstellensatz. So first still these general things, but okay, quite interesting. So one definition. So this is not really related with our main topic, but this is related about other ways of showing compactness theorem, and then about some of its consequences and maybe even philosophical connections. So, okay, let phi L sentence, L is some language, T L theory. So we say that T proves phi. Before there was a notion that phi is a logical consequence of T. It meant that in all models of T, also phi holds. So this was something which was a connection, which was in a way that T implies phi before, but using structures. Now it will be something similar, but purely syntactically, so without any models. Okay, so T proves phi, and it is denoted like this. Before there were two lines here, now only one. Okay, and now I have to be vague, because the formal definition will be pretty long. So if there is a finite logical proof showing, so I will give examples what this can mean, showing that phi follows from a finite subset of T. So the difference is there are no models involved. It's just kind of pure logic. So this finite logical proof in fact means that there is a list of legal logical arguments which we can do to derive some sentences from other sentences. So this means.
What does syntactical mean?
Huh?
What's the difference between syntactical and semantic?
Yes, that's if I remember correctly, syntactical is exactly this. It's some formal argument using these laws of logic I will mention. And semantical uses some structures. So some interpretations of this into structures, let's say something from more real world kind of. And this is more formal. So another name, so there is a list of so-called rules of inference. So to infer means to conclude in purely logical way something from something. So I will just examples of some of these rules of inference. Okay, so all of them are pretty obvious. Such rules that everybody has to agree this can be used. For example, if theory T consists of two sentences alpha phi, then we can infer from it that conjunction holds. If two of them are here, that conjunction is logically implied by both of them. Yes. If there is only one, then this junction and something slightly more complicated, but not more. If alpha is in this theory, if the implication alpha implies beta is in the theory, okay, so now all of those are of course sentences. Then we can infer that then this kind of logically implies beta. This is something called modus ponens. And obvious things like this also involving quantifiers, etc., etc. There is kind of complete list what really can be used. So this one is often confused in real life because people like to think that this is true, but not. Assumption has to be true, and the whole implication has to be true to conclude the conclusion. Yes. In real life, people often forget about this part, especially on television, etc. Okay, and then what is interesting about this, that Gödel proved. So the following theorem is closely related to compactness theorem, and this is how Gödel proved it. So Gödel completeness theorem
I didn't understand the second example.
Because this is OR. Yes, so
Okay.
when OR is true, if and only if one of them is true. So it's totally, I mean, everything should be here totally obvious if we correctly understand the meaning of this. Yes. Yeah, I'm not sure if this is even official inference rule. I just wrote some. This definitely is. This also. There is some finite list such that this theorem holds, and this theorem says these notions are equivalent, which is totally non-obvious. So like semantic and syntactic is the same. So one direction is quite true. This direction would be obvious if this inference rule are kind of logically obvious. Then in every model when T holds, also phi must holds, because it's implied by these rules. But the other way, that if this can be checked on models, then also there is this purely logical argument. So that means that this list of rules must be kind of complete, that all possible, the kind of all mathematical proofs really can be done using these rules of inference, which we don't really do in real life because it will be like even easy exercise would consist like of 1,000 inferences. Of course, we script it in there. But the theorem says theoretically it can always be done, and even such a thing can be maybe checked by a machine if it's correct or not. So that makes us.
When you interpret this phi in every model, if
yes.
it's true, then phi is
logical consequence by sum of list, long list. So there is. Yes, it's totally non-obvious. Checking here, and then that really exists this finite sequence of these inferences. Yes.
Logically true
Yes, so sorry. So there's a definition of this. So I think this is the semantic. Okay, so theory T proves phi if there is a finite subset of T such that using finite list of rules of inference, which I just gave examples, it can be obtained. Of course, at each step we add this new one. Yeah, so this is something like purest proof, okay? But okay, it's kind of as opposed to problems with ZFC. This is something to which we can sleep easier, to know that if there is a proof, we should be always able to write this finite list and really check it, okay? And then nobody does it, but at least she's... So as I said, Gödel actually proved compactness theorem using completeness theorem. And for you, I have a problem. So now there will be several problems, pretty abstract. None of them difficult, but it may be not so easy to kind of jump into this kind of thinking. So problem 10, assuming Gödel completeness theorem show that the following are equivalent. One, T has a model which we know by compactness theorem is equivalent to that T is finitely satisfiable, and then T does not prove anything contradictory. Okay. Some obviously contradictory statements, so if one wants to specify it, okay, let me specify it. So that is it is not true that T implies something like phi. So that T proves something like phi and not phi. So statement like it is the best would be to say something like here it is not true that 0 equals 0, but maybe there is no constant in the language, so it's hard to say. But you can always imagine there is some obviously contradictory statement in the language, so such a thing should... 0 equals 1 is okay. It's sometimes true, but not true that 0 equals 0, that 0 not equal to 0 is definitely wrong. Yeah, 0 equals 1 is perfect, 0 ring. Okay, so this is a problem, which is very easy, but and it does not use compactness theorem, just completeness theorem. So now, okay, the definition. Yes, but again, this is so still the compactness theorem was equivalence between two syntactic statements about the existence of models. And this is something else, equivalence of syntactic. There is some model we can check. And this, there is no finite proof showing something contradictory. So this is purely formal, these two. No models are involved. Okay?
This is for computers.
This is for computers, however, yeah, I will talk about ZFC a bit. I mean, it's hard for a computer to show that there is no finite proof showing something, because computer cannot check all finite things.
Yes.
Computer may stupidly, by chance finds this contradictory statement, but probably not. But it cannot show the otherwise. Okay. Computer may check if our candidate for such a proof is correct, but I doubt if it can find such a proof. Okay, but who knows what they will be able to do. So my definition is that T is consistent I mean, if it satisfies this equivalent statements or the one from there. So if it satisfies this. Okay, so this is consistency. Okay, so let me just say that by compactness theorem, actually three things are equivalent. T is finitely satisfiable, T has a model, and then this third one, T does not prove any nonsense. Okay, and then we call such a theory consistent. Okay, so still one more remark not related to our topic. So, of course, big question is, is the theory we assume to work at all in mathematics consistent? So now at least the question makes sense, because if we used models, we could ask, okay, but to create models, you use ZFC. So how can you ask about consistency of ZFC using models? But using this is well-formed question. So question is there a finite subset of ZFC and a finite proof showing like that empty set is not empty? Yeah, this is perfectly clear absolute question, not related to ZFC. And I think we should, it's either true or not true, as all questions in life. So definitely there is some answer. I mean, okay, maybe there is a, what is this? This question has a truth value. True or not true?
So it can be answered.
Well, that's the other question. I disagreed with my advisor Ludomir Neversky a bit. So, okay, we agreed. Okay, so there are two cases. It's consistent or inconsistent. We still agree with that. Okay. And okay, if it's not consistent, then one day we can find this proof, which everybody will be able to check.
That the empty set is not empty.
That the empty set is not empty. And this is what usually happens to us when we try to solve a problem and suddenly there is some contradiction, we don't know with what. Then, of course, we may think maybe we found contradiction in mathematics, so that FC is inconsistent, but it means we made a mistake in most of the cases. But okay, if we didn't make a mistake, it would mean we found a contradiction in mathematics, which means, so yeah, so that's the slang contradiction in mathematics would be such a proof of inconsistency of ZFC, which one day may be found. This is possible. And then, okay, I think if it is consistent, okay, then I think we will never learn it because of something called Gödel's incompleteness theorem. Okay, so Gödel. But this incompleteness, there are two actually. This theorem. It says that if one can show, okay, because again, sorry, this finite proof will not use ZFC. It will be finite sequence of inference rules, not ZFC, just finite string of symbols. But the actual proof of consistency, Okay, in my perspective, it has to use ZFC. It has to use our mathematics. And then Gödel completeness theorem says that if one can show consistency of ZFC, well, using ZFC, then ZFC is inconsistent. So actually, it will be proof of that. Okay, but still one can think, as some people think, that we are okay. In reality, we are not really checking axioms and doing something. We are making discoveries. So one day, we can make a possible discovery that ZFC is consistent, but it would mean we accepted some bigger theory, which became somehow evident that we should use the other theory, bigger than ZFC, and inside it prove ZFC is consistent. But then the same problem would remain about the bigger theory. We will not be able to show this is consistent. So my answer is, if ZFC is consistent, then we will never know. But it's kind of philosophical, what is a discovery in mathematics, okay? It may become evident for us on some grounds that it is consistent at some point, because we start to believe in some other theory, okay? So that is maybe something, okay, but on positive side, I think kind of time tells. So like the ZFC exists for, I don't know, 180 years, and it has no proof of inconsistence, so the probability grows that there is no such proof. Huh?
Any theory.
No, any theory, okay, yeah, in soft piano arithmetics. So the thing is, any theory which can formalize its own proof, kind of, which can formalize this performing proofs inside it, kind of. It can be. So, okay, I would have to talk about this theorem. So also piano is the same with piano arithmetic, for example, which you can, this sequences of proofs you can formalize inside piano arithmetic, and still you cannot prove inside piano arithmetic that piano arithmetic is consistent, but you can prove it inside ZFC because you find the model natural numbers. Okay. So there is a notion of some expressive power of a theory. Basically, we can formalize proofs using. Okay. This is not our topic, but somehow it comes naturally here. Okay. So these are kind of our boundaries, how much we can be sure that what we are doing is meaningful.
I'm asking if I understand clearly. When I'm trying to understand T, whether T proves phi, I'm thinking all the formulas in T are of value 1. They're
good. Yeah.
So I'm trying to get the result is true, right? Basically,
No, so
he doesn't have truth values.
No, but it's kind of okay. You can assume all of them have value 1, and then it's okay. And then this 2 is true if you cannot get value 0 by inference rules.
I didn't understand.
So, for example, if your theory T, okay, if your theory T is alpha and not alpha, okay, then you assume all of this has value 1. Why not? But then it implies alpha and not alpha, and this has obviously value 0. Okay, absolutely 0, because this you assume is 1. Okay, so this is not absolute, but this is something which is just always false. Okay, so the point is that from your assumption that everything has value 1, you cannot get anything which has absolutely logical value 0, like such a thing.
If I want to think like that, T must be consistent.
If you want that really it has value all of them have value. I mean, not necessarily. Okay, yeah, but still, such a theory, there are models such that alpha is true, and there are models probably such that negation of alpha is true. So you cannot say that both of them are kind of zero. They are just sometimes true, sometimes not, possibly. But this is always not true. So the point is you cannot obtain something which is always not true.
So you cannot obtain this, right?
Yes. I mean, you can, from this theory, you obtain this. Because it's inconsistent.
Okay.
From an inconsistent theory, you can get anything, any sentence.
Yeah, but for example, there is no model, of course, of this sentence. That means it has kind of absolute logical value 0.
Maybe I didn't understand the definition of T proves phi.
Yeah, because I didn't give all the rules. So there is a finite subset of T, like phi1, phi(n), and a finite sequence of inference rule, such that first one takes some of this phi1, phi(n), and gets you phi(n plus 1. Then you add phi(n plus 1, and continue. You get second one, which gets you phi(n plus 2, and at the end, you get this. So, I mean, okay, in general, you get this phi, which you wanted.
Until the last line of the proof.
Yes.
And the proof is finite, it's very important.
Okay. I mean, is there anything else? There is nothing else, I guess, right? You are taking phi and you decompose it with this atomic things.
You can think something else, in which sense?
Huh?
What did you mean by something else? No, there are other inference rules, of course.
What else?
I was at this webpage today. There was about 20 of them. You have to talk about quantifiers. So if there is some instance which is true, the formula exists is true. For negations, I mean the inference rule for negation, basically you describe all of this. Maybe not all is necessary. All of the kind of obvious properties of these quantifiers using rules like this.
And also modus ponens. Alpha is
Yeah, so it's.
Okay.
So I guess it's for this and this kind of, but. But naturally is to include it. Yeah, you may check. There is rules of inference on Wikipedia. I'm not sure if they are minimal, but there were quite a lot. It's not very important what they are, but this theorem says that they really work. Yes, there are really enough of them to have this equivalence. Okay, and this is something we will not be interested in. Okay, we work under ZFC and then want to actually prove real theorems about fields and other things using model theoretical tools. So some more general definitions which now will be useful for us. So definition T is complete. Theory is complete. Let us not forget if it is consistent. And for any L sentence phi. So not necessarily it must be here or negation, but it is logically implied. So okay, so we will be using this. It's equivalent, but this semantic thing. We have that phi is a logical consequence of T or its negation. Yes, so nothing is kind of independent. So remark for examples, this maximal. In maximal theory, we had just that phi is here, or negation is here, so it's stronger. So maximal consistent theories, like a theory of a structure, are complete. But this is much more meaningful notion. Completeness. Yes, because if you have given a theory by a list of axioms, it's almost never maximal, but it can be complete, as we will very soon see about algebraically closed fields. Just we don't really care about all the logical consequences. Just enough to axiomatize it in a complete way, such that all of them follow. Okay, and the other thing is, so we don't know that ZFC is consistent, but it is known that. So I think this is last remark about ZFC. ZFC is not complete. Yes, that was the first, and then lots of. Yeah, and then, okay. So this is set theory. It is well accepted, but one can think, okay, how do you prove that something is independent from ZFC, not using ZFC? And there are ways to do it, and this is what set theory does. Okay, so somehow, okay. So always we can worry, but in practice it also doesn't happen. If you have some real actual mathematical question, theoretically may happen that there is no answer that is independent from ZFC, but in reality it doesn't happen.
The incompleteness isn't it from maybe I'm asking a stupid question. You're done because
No.
recursive, isn't it recursive?
No, it's just the other usage of the word. He's talking, I think, about incompleteness of predicate logic or something.
No, piano arithmetic is not complete.
Piano arithmetic.
There is any recursive theory containing piano arithmetic is not complete.
Okay, right. That may be second Gödel's. Maybe you are. And this is okay. I think that may be second Gödel's incompleteness theorem. Right. Okay. So maybe it is here.
This is second. This is the second argument.
Okay, there are two definitely. Okay. One is about this. Okay. Right. Okay, so then, okay, but then, so maybe continuum hypothesis was the first natural statement, and before it was known abstractly. Okay, good point. Yeah, it's not something I know a lot about. And last two problems about such things. So problem 11. And they will be even used in the proofs later. So assume T is a consistent theory. And then the following are equivalent. T is complete. And we can check it on models. So for any L structures Mn, we have that if they are both models of T, then they are elementary equivalent. So they satisfy the same sentences. Yeah, it's not difficult. Okay, and one more problem about complete theories. So now assume that T is complete. Phi is a sentence. First thing, if M is a model of T, then phi is satisfied in M if and only if phi is a logical consequence of T, and phi is a logical consequence of T if and only if we add phi to T, it is consistent. Okay, so such things we usually assume without much thinking, but it should be proved once. Okay, so this is all about compactness theorem and related concepts. So now we proceed to show these theorems MT1, MT2 from the first lecture. But we need some notion related to substructures. So unfortunately we need some more abstract definitions. Okay, so proceed to proofs. That's a general concept, but still, okay, one more or two more notions. So we have some language. We have two L structures. Okay, so as in algebra we would like to talk about homomorphisms. Here somehow, because of relations, there may be some problems if the function is not one-to-one, so we will only define notion of monomorphism. So a function phi. Yes, so there is no theory so far, just structures. From universe to universe is an L monomorphism. Okay, if of course, okay, so if phi is of course one-to-one, and in short, but I will define precisely, preserves interpretations of symbols from L, which means So for any function symbol, relation symbol, and constant symbol, something obvious must hold. So for each f in f, for each function symbol, let's say of arity n, and all things from the domain of its interpretation, for all m1, mn in M, we have that if we apply this function to the value of the interpretation of f in M on this n tuple, it is the same as we apply interpretation of f in n to the n tuple of values of phi. So here, diagram may be useful. So in other words, such a diagram that is, here we have this m to the n. We apply interpretation of the function symbol f in M. So we go to M. It's like addition or multiplication. Here we have psi. Go to n. And here we have nth Cartesian power of psi. So this should be commutative diagram. If you think about what is ring homomorphism, it would be exactly this for two function symbol plus times. So now relations and some tuple n tuple on which relation may hold or not. So now it's kind of different sort. It holds in M if and only if it holds in N. Yes, so we also care that we don't want that somehow this relation in N has more things inside possibly coming from M. Okay, if and only if. And for constants, the obvious thing, like 0 goes to 0, 1 goes to 1, properly interpreted. Okay, so this is it. So before break, okay, some examples. So examples are obvious. So ring group. Okay, this mono. Are L monomorphisms for appropriate L. And for example, one-to-one functions, preserving order. Yes, if we have a language of orders, then it should be a function one-to-one which preserves order, like embedding natural numbers to rationals or reals. Okay, maybe we have a break now.